Hi everybody, it's Ms. Frazita. We're looking at section 8, which is derivatives of inverse trig functions. And first I have to say, well, we've already got the derivatives of all 6 of the trig functions, and so now you might be thinking, oh, inverse trig functions, 6 more formulas. I guess the good news is that you actually only have 3 formulas to memorize as opposed to 6. And I'll explain why in just a minute. Okay, so first of all, I know inverse functions may have been a while ago, and I don't want to assume that you remember them. So here's a quick review, just what inverse functions are. So graphically, if you have the inverse of a function, then what you're doing is reflecting the curve across the line y equals x. So whatever your original function is, picture the line y equals x and reflect it across that. The new picture you get would be the inverse of it. Now, the slope, of course, is of interest to us because here we are in calculus looking at derivatives. Derivatives is slope. So when you're thinking about reflecting it across that line y equals x, what you're really doing is remembering that x and y are trading places because you're reflecting it across that line. So, and in fact, that's algebraically how you would find the equation for the inverse if you ever wanted to. X and y would trade places. You'd solve for the new y. So when you're thinking about the slope, whatever the slope of the original function is, the new function will just be the reciprocal of that. So again, our original function would be whatever dy over dx is, or delta y over delta x. And because x and y trade places, the domain and range trading places, the slope flips over. The x's are on top now and the y's are on the bottom. And so that really is just the reciprocal of the slope. Now don't be confused or get confused with perpendicular, right, which is opposite reciprocal slope. This is just simply reciprocal, okay, no negative sign. The last part down here, I put in the little theorem that's in this section that says as long as the original function slope is not 0 and it exists everywhere, then the inverse function will also exist and be differentiable. Now, of course, if the original function slope is 0 at some point, so here's our original function slope, if it equals 0, then the reciprocal of 0 would be undefined, and that's why it would be a problem. So as long as the original function slope is never 0, then it's going to have an inverse function and it will be differentiable. Okay, so here are the 3 formulas. Again, I know there's 6 trig functions, but actually you just need to memorize these 3. These are not pretty to memorize. I do actually go through the proof of one of them in case worst case scenario you can't remember one. You can always derive it. Like I said, worst case scenario. But if you can memorize these 3, that would save a little time. The reason why you don't have to memorize the other 3 is because the other 3 are just the co-functions of these 3. So cosine, cotangent, and cosecant. So there is a relationship between the function and its co-function. And with inverse functions, all the co-functions are really just equal to pi over 2 minus the actual function. Now, these are not derivatives. These are just straight up what they are equal to. So if I'm ever interested in the derivative of cosine, I can take the derivative of this part over here. And of course, the derivative of pi over 2 is nothing. So really, the cosine's derivative will equal the same as the sine's inverse derivative, except it will have the minus sign out in front. So if I back up, so here if you can memorize that this is the derivative of inverse sine, then cosine inverse derivative will just be negative of the same thing. Okay, so here we are. Let's try an actual problem. I put at the top the formula for the derivative of inverse sine, just in case you didn't instantly memorize that. So our actual problem, though, here we are given inverse sine of 1 minus t. We're looking for its derivative. So the 1 minus t part is actually what we have for u. So when you see a u over here, I have to replace that with 1 minus t. Also, this part over here is our chain rule part where we have to take the derivative of 1 minus t, which in this case, 1 minus t's derivative is negative 1. Okay, and I get basically this. And I just squared this out and combined my like terms to get my answer. The other thing I didn't really talk about before is this little part over here, the condition the absolute value of u is less than 1. They're just putting that in there to make sure that your square root comes out a positive underneath there. What's underneath the square root needs to be positive. So as long as u is a number smaller than 1 or absolute value is smaller than 1, then when you do 1 minus it, you'll have a positive number, squared. Anyway, you'll have a positive number, and you won't be taking the square root of something that's negative. That's the only purpose of this part over here. Okay, let's try another one. So this one looks a lot more complicated. Here our original equation for y is tan inverse of this thing plus cosecant inverse of x. And they do say in the initial problem where x is greater than 1. Okay, so let me just, I thought I could move that out of the way. Oh, I can't move it. Okay, so anyway, when I'm looking at the original problem, it's got a co-function in there. And again, I don't have a straight formula for derivative of cosecant. So I'm going to switch cosecant to pi over 2 minus secant, which is what's kind of hidden underneath there. So pi over 2 minus secant x. That's what I'm plugging in. Now I can go ahead and take the derivative. So derivative of tan inverse, I went ahead and wrote my formulas down again for you. So derivative of tan inverse of u is 1 over 1 plus u squared. In this case, the u is square root of x squared minus 1. So again, my derivative will be 1 over 1 plus that whole angle thing squared. And then this du dx, I have to do the chain rule, so figure out what the derivative of u is. So again, the derivative of my angle here, this is a 1/2 power, so a half comes down. I do power rule, rewrite the inside, subtract 1, so you get negative a half, and then times the derivative of the inside is 2x. So this entire thing, including that 2x, is the derivative of the angle. Okay, so plus, and then I take the derivative of the next term. The derivative of pi over 2 is just 0. And then the last term, I take the derivative of negative secant inverse. And again, I put the formula down here for the derivative of secant inverse. So notice the minus sign I carry down. It's minus because it's secant, not cosecant. Or it was cosecant, not secant, however you want to look at that. Let's see. So looking at this part right here, that should match up with this. We already know that x is greater than 1. I didn't really bother putting in the absolute values for x because we already know x is a positive number from the given here. But you can put the absolute values in there if you really feel like it. Okay? And then the rest of it, I guess I'm not going to take too much time to go through it. The rest is just simplifying it down. It does turn out 0 in the end because this part and that part are the exact same thing. Okay, let's try a different one. So this one looks quite different. Here they're giving us a nice simple looking function for f of x. And then there's a part A and part B. So part A is just asking you, what's f of 1 and what's f prime of at 1? So f of 1, that's just your straight, plug 1 into your function and see what it comes out. So here's my function. I plug 1 in, 2 times 1 cubed plus 1. That gives me 3. And f prime of 1 means the slope when you plug 1 in. So I took the derivative, getting 6x squared plus 1. And then I said, okay, well, I want the slope specifically when x is 1. So I plug 1 in, 6 times 1 squared plus 1, I get 7. So nothing new really at all in that part. So you go on to part B, and B says we want f inverse of 3. Now because I've already done part 1, I know that on the f function I have the point 1,3, which means when x and y trade places to get my inverse function, I have on the inverse function the point 3,1. So here I'm supposed to recognize from part A that since I'm switching the x and y coordinates, that this must equal 1. Over here with this, this is the slope of f inverse at 3. Well, if you think back to what we said before about delta y over delta x, x and y trading places, you really get the reciprocal of the slope. So here, I already figured out at the point 1,3 on the f function, my slope was 7. So at the mirror image of that point, which would be 3,1, the slope will be the reciprocal, 1 over 7. That right there, if you can remember that, that might save you a lot of time on your chapter test as well as on your AP exam, because I have seen or have known that to be on the AP exam, where people actually sit there and try to figure out what the inverse function is, and then take its derivative and then plug in 3. And if it's hard to find the inverse of the function, it can be kind of tedious and slow, where this is just real quick, 1/7. Okay. So I thought I'd go ahead and put one of the proofs in. I have to tell you, all 3 of those derivative functions proofs are in our section in the book, so you're welcome to read through the other 2. I thought I'd at least walk you through one of them. That way, if you're like me and have a hard time memorizing things, that worst case scenario, you could derive it. It's not too bad. You can tell the steps are not that long. Okay, so first of all, let's say I'm working for sine inverse of u, or sine inverse of x, to simplify things. So let's say I'm trying to come up with the derivative for sine inverse of, let's just say, x. So what I first do is call that y, and then I'm going to go ahead and take the sine of both sides. So sine of y on the left, and sine of sine inverse of x just gives me x. And then I need to take the derivative. So on the right side, the derivative of x is just 1. And on the left side, the derivative of sine y, okay, will be cosine of y chain rule times the derivative of y. And if I get derivative of y by itself, I just divide through by cosine y. Now cosine y with Pythagorean theorem, right, sine squared plus cosine squared equals 1, our Pythagorean theorem, 1 minus sine squared square rooted would be cosine y. So I substitute that in there. And last thing, sine y is defined to be x. So I go ahead and replace sine y with x, and there's our formula. Now again, I didn't look at u, I just called it x. But if this right here is not just simply your variable x, maybe it's x squared or x cubed or something like that, then don't forget you would have your chain rule part. You'd be taking the derivative of whatever that part there is. Okay, and that's it. Okay, so I have 2 problems for you to try. Remember, go ahead and hit pause, really try them yourself, see how you do. You can look at your formulas from the notes, and then after you think you got it, go ahead and hit play again, and I have the answers in a sec. Okay, let's try the first one. So I'm looking for cotangent inverse of this. So the co-functions, remember, are pi over 2 minus the actual function. And then when I take the derivative of the pi over 2 goes away. The minus sign I left out in front. And then I use my formula for the derivative of tangent, tan inverse, which is this formula here. Okay. Okay. Sorry, I think I lost a minute there. Looking at the derivative, you would have the derivative of pi over 2 goes away, and then the derivative of tan inverse, you leave the minus sign out in front, and you're just using this formula down here. So this u part is the angle, which is root t minus 1, and then don't forget the chain rule, du dx, which requires power rule, so a half t minus 1 to the negative a half. The rest of it's just simplifying. Okay, let's try the last one. So for this one, I have sine inverse of 3 over t squared. So here's our formula on the side. I go ahead and plug my 3 over t squared in for u, and that's there. And then also I need to take the derivative of the 3 over t squared. So derivative of 3 over t squared, again, think of it as 3t to the minus 2, and do your power rule. So negative 2 comes down, making 3 times negative 2, negative 6, t, and then subtract 1 from the exponent. This one, the simplifying, oops, sorry, go back. The simplifying on this one actually was a little bit tricky. This part to here, I guess, made sense. And then from here to here, I found a common denominator underneath my square root of t to the 4th power. And then if you think of that t to the 4th as a common denominator, you can actually pull it out of your root as t squared. So this t cubed that's already outside being divided by t squared gave me a t. And that's how it's simplified. Okay, we're all done. Thanks.